Every website lives somewhere. When that somewhere is thousands of miles from your user, the journey becomes painfully slow. A single origin server in one country forces every visitor to haul data across oceans, losing hundreds of milliseconds to physics alone. This is the problem CDNs were built to solve. Anycast turns one IP address into many. The same number is announced from data centers in Tokyo, London, Sao Paulo, and Sydney simultaneously. BGP, the Internet's routing protocol, then hands each user the shortest topological path. So 4 different people type the same address and reach 4 different machines, each one close to home. These distributed servers are called points of presence, or POPs. A modern CDN operates hundreds of them across every continent, turning a transcontinental crawl into a neighborhood stroll. The more POPs, the smaller the average distance between content and consumer. Each POP caches content at the edge. The first request arrives cold, a cache miss, so the edge forwards it to origin, fetches the asset, stores a copy, and returns it to the user. Every subsequent request is a cache hit, served instantly from local storage without ever touching the origin again. But what decides whether a request hits or misses? The cache key. It's a fingerprint built from the URL, selected headers, and query string. 2 requests with identical keys share the same cached object. Change a query parameter and you've built an entirely new key, which is also why CDNs expose purge APIs. Developers push a button, the stale fingerprint is invalidated, and the next request fetches fresh content from origin. One last layer keeps the origin sane. The origin shield. It sits between the edge POPs and the origin, aggregating cache misses, so that 100 simultaneous edge misses collapse into a single upstream request. The shield also absorbs traffic spikes, smooths thundering herds, and adds a final defense against overload. We are going to poke at a real CDN, cdnjs.cloudflare.com, using only built-in Linux tools. By tracing DNS, measuring latency, and reading response headers, we will see where our requests land, and whether assets come from a warm edge cache. We start with a clean terminal so each command and its output stand out clearly. From here, we will run a small stack of utilities, ping, curl, and grep, none of which require any installation. First, we ping the CDN hostname twice. Because Cloudflare uses Anycast, the same name resolves to the nearest healthy POP, so a low round-trip time here is our first hint that we are talking to a nearby edge rather than an origin data center. We also ping 1.1.1.1 directly to establish a local latency baseline. If the CDN hostname responds in roughly the same range, the Anycast route is clearly landing on a close POP rather than some distant origin server. Now we fetch only the response headers for a popular jQuery file with curl. This is the moment of truth. The headers will tell us the edge server's name, its CF array identifier, and the all-important CF cache status that reveals whether we got a hit or a miss. Rather than scroll, we pipe the same curl into grep to pull out only the lines that mention cache. The CF cache status shows hit, the age is over 1,000 days, and the cache control is set to immutable. This file is living permanently on the edge. We repeat the header check on another well-known library, Lodash, and confirm the same pattern. HTTP 200, a hit cache status, and a large age value. This is exactly what we expect from a hot, globally cached asset. Every Cloudflare POP already has it. Finally, we request a file that does not exist, capturing only the HTTP status code. We get a clean 404 from the edge, no origin round-trip needed. Proving the CDN serves even its error responses from the nearest POP, which is the whole point of Anycast edge caching.